All right, welcome. In this video, we're going to be practicing for the Chapter 4 test about exponential and log functions. And so we're going to be going through a set of practice problems that are from AP Classroom. They're from the Personal Progress Check. And, like I always say, these are questions that are definitely relevant to the test, but the questions that are most relevant to the test are the ones that were on the quizzes throughout the unit. All right, so let's get to it. The number of bacteria in a dish is 1,150 at time 0. The number of bacteria in the dish doubles every 3 hours. So we know our formula for b of t is going to be the starting value, 1150, times some number to the t power. And I think what I'm going to do is I'm going to use the information that they gave me. Doubled after 3 hours. Well, that means that b of 3 is going to equal, well, 2,300 if I double 1150. Okay, so, but if I plug in 3, I'd have 1150. Now I was trying to figure out what letter to call that. I don't want to call it B, and it's usually what we would do. Let's call it U. Okay, so U to the third power, because t is equal to 3. And so now we need to figure out, what's the value of U. And we divide 2,300 by the 1150, and that's going to be 2, like we expected. It doubled. And that's going to be 2 equals this base cubed. So I would take the cube root of both sides, and I get the cube root of 2 equals U. As a result, I know now that b of t is going to equal 1150 times the third root of 2 to the t power. And I did not look at the answer choices. Okay, so that's not, like the most useful thing ever. It's not one of my answer choices, right? Well, this is not 2 to the 3 to the t, right? Because that'd be 8 to the t. I think it's going to be answer choice D. I can kind of see that it's going to be that. I think maybe I could have said or u equals 2 to the 1/3. And then I think if I'd written this as 2 to the 1/3, then on a multiply the exponents level, you can see why it's 2 to the t over 3. Yeah, that's going to be D. And that's, I think, all I've got to say about that one. We've got a good number of problems in this set. So f is given by f of x is some number k plus a times b to the x. Okay, so it's an exponential that's been shifted up or down by some number. Okay, which of the following is true? And so we're talking about limits as x approaches infinity and negative infinity. All right, well, we're saying, first thing I'm noticing here, b is greater than 1, which means that this thing is, whoops, I meant for that to be a blue pen. This is exponential growth. Okay, if it's exponential growth, okay, it's not the worst one I've ever drawn. We know that the graph kind of looks like that. Okay. This is just y equals a times b to the x. Right? Plus k, we're going to go up and down by a little bit. But the limit of this thing, as x approaches infinity, is positive infinity. So I don't see either, both of the c and d are talking about x approaches positive infinity, and f is not approaching positive infinity, so I'm going to get rid of those. Right? I'm going to say as x approaches negative infinity, a times b to the x, with b being greater than 1, that's going to go towards 0. It's got that horizontal asymptote y equals 0. I can think about when x is a negative number, I'm doing a divided by some power of b, and as that power of b grows, I'm going to be taking, it's a fraction where the numerator is constant, the denominator is growing, that goes 0. Okay, but if I was to bump this up or down by k, that's kind of what they're asking, limit as x approaches infinity of a times b to the x, and then add k off to the side, well, that's going to equal 0 from up there plus the k. About like that. So I think what I'm going to say is that as x approaches infinity, f is going to approach positive k. Oh, whoops, again, the pen versus highlighter issue. Okay, I want that answer right there. Right, a hobby shop wants to attract customers on slow sales days by offering a new discount. Shop offers a 1.5% discount on Wednesdays with an added bonus for repeat customers. Customers who make the purchase on successive Wednesdays get their discount doubled from the previous one. So, for example, certain customer makes purchases on 3 successive Wednesdays and gets 1.5% the first week, 3% the second week, and 6% the third week. Based on this pattern, what is the first successive week that a customer's discount would exceed the purchase price of the item? And I think that would be like, when does this discount go beyond 100%? And I don't know what else to do here besides just make a table. I'm sure there is probably a better way. I'm just going to say week and discount, right? So week 1 was 1.5%. And, I think I'm just going to measure that in percents. Week 2 was 3. Week 3 was 6. And we're just going to keep doubling. 48. 96, we're really close. Okay, so this one is going to be greater than 100% discount. Okay, so that would be 5, 6, 7. Week 8, that's the first time the customer's discount would exceed the purchase price of the item. Okay, so that would be answer choice C. All right, then number 4. G is given by 4 times 2 to the power of 3 plus x. Which of these other ways can we also express g of x? Okay, so it's been a while since we've done this, but if we say 4 times 2 to the 3 plus x, if we're adding exponents, we can look at that as a product, right? 2 to the 3 times 2 to the x would be where we would add those. And we know that 2 to the 3 is 8. Okay, and then we could just, associate whatever we like. 4 times 8 is 32 times 2 to the x. That's going to be answer choice B. All right, now h is given by a times b to the negative x, where a is negative. Oh, okay, interesting. A is negative and b is greater than 1. Okay, well, if a had been positive, I'd been thinking, okay, b greater than 1, b to the negative x, that's exponential decay. So this is, I'm just going to say y equals b to the x. B to the negative x. And that would be exponential decays. That's really low, but okay, that works. Okay, that's my exponential decay curve. If I had y equals a times b to the x, and a was a negative number, the a part, if a is, whatever the actual absolute value is, that's going to be a vertical stretch factor. But then the fact that it's negative is going to reflect across the x-axis. So I'm going to go down here and say, all right, now I'm looking at one where, okay, it's going to be flipped over the x-axis. So it'll look like that. So I'm seeing that this graph, as I move left to right, I'm going uphill. So that's increasing. Get those out of here. And the graph is concave up or down. Well, that's the attitude. Now, if I put the eyes over the curve, it looks like the thing's frowning, so that's concave down. And so concave up is out, and there we go, like that. Right, next, students in a stats class examined individual student test scores for a large group of students. Each test score was paired with the reported time the student spent studying. Class observed that when study time doubled, test scores increased by 5 points. This one is clever. I would not have thought of this example. I like this one a lot. For example, a student who studied 2 n minutes generally scored 5 points higher than a student who studied for just n minutes. For non-zero constants a and b, which of the following types of functions is most useful in modeling test scores? Okay, what I'm going to do is I'm just going to give you a couple of examples in minutes, or I guess n is probably, use t in minutes, and y will be the score. Okay, so if we think, okay, study time doubled, t will just be, I don't know, maybe in hours, and maybe 1 hour got you, I don't know, a score of 70. And if we doubled the amount of time, score goes up by 5. Okay, this, I don't know. Who knows? Maybe my starting value of 70 was a little too low, but I don't know what kind of stats class we were talking about here. So maybe that's, and we got to double the amount of time, 8 and 16. And this is where we're seeing one of those tables where it looks like an exponential function in reverse, right? Y is a function of t. So if the input, if the input values are multiplying, okay, I need to probably call that times 2 like that, times 2, times 2, and times 2. If the input values are multiplying, but the output values are adding, that's going to be a log. That's, if you go back to the notes, that's kind of like one of the primary things we saw about log functions is that equally spaced outputs correspond to multiplicatively spaced inputs. Okay, so that's all this to just say, okay, I'm looking at a log function because of that, and it's going to be answer choice B. All right, now here is a table of values for a function f at selected x values. Which of the following statements and their reasons are going to be correct? Okay, 2, 4, 8, 16. This is the exact same thing we just saw. X values are multiplying times 2 times 2 times 2. Y values, output values are adding plus 3, and plus 3. Okay, exponential growth, no, it's going to be logarithmic growth, so I'm going to just get rid of these answer choices because it's saying exponential. As input values change additively, input values are not changing additively, input values are changing multiplicatively. Yeah, output values change additively. Okay, so that was answer choice D. Let's keep moving. Function f is, again, another question about the same property. Kind of wish I'd looked at these a little sooner and grabbed a couple of them for the test. Okay, each time the output values increase by 4, the corresponding input value is 4 times greater. Inputs are multiplying, outputs are adding. Okay, so it's got to be a log function. And so the only ones that are looking like log to me are A and B, right? C and D are looking like exponential growth. So what I'm going to do is I'm going to say, all right, well, each time the output values increase by 4, okay, well, I'm having a hard time on A seeing a place. Okay, the only like grid intersection for the outputs I'm seeing is right here and right there. But that's not increasing the output by 4. Output is Y. That only increased by 1. Okay, so I'm thinking it's got to be B. Okay, output values increased by 4 when I went from, when X went from 1 to 4. Okay, okay, right here, X equals 2 to X equals 8. I went up by 4 from 2 to 6. Okay, that's plus 4. You can't really see that. And then I'm going to say, okay, over here. Wait, that's, that's what I wanted to show. Plus 4 over here. That's what we've got. I think I've talked about that one enough. All right. F is given by -3 times log base 2 of x plus 1. Which of these limit statements describe the end behaviors of f? Interesting. Okay, I guess we need to think about this in terms of the transforms. So if I had f of x, maybe not f of x, I might call it y equals log base 2 of x. Okay, what that's going to look like is that, right? It's going to have, as x approaches infinity, y approaches infinity. And as x approaches 0 from the positive side, y approaches negative infinity. Okay, but if I do y equals -3 times the log base 2 of x, it would get 3 times as tall and be flipped upside down. So that means that, this part I'm circling in red, where I had a vertical asymptote going down, I'm not going to have a vertical asymptote going up, right? Because it just made it upside down and scaled up by a factor of 3, evidently. Okay, so I'm going to circle that way. And then if we're going to add 1 to it, well, that's just really not going to look all that much different. And what I might do, adding 1 would just be like that, right? If I just scooted the graph up by 1, and the x-axis would look like it went down by 1. And so that's my new graph, and that's going to be good enough. Right here, we can see that red circle is saying the limit as x approaches 0 from the positive side of f of x is going to equal positive infinity. Okay, so let me look at that. Yeah, that's D, right? I don't need to look at the other ones. I mean, the second limit is true. As x approaches infinity, y is going down very slowly. But that one is true because of that. But yeah, there was only one that had x approaching 0 from the positive side and the limit being positive infinity. Okay, so over here, f is given by log base 2 of x plus log base 2 of x minus 2. What makes f of x equal 3? This is just an equation we will be able to solve. Okay, so log base 2 of x plus log base 2 of x minus 2. That's f of x, that's going to equal 3. Now I'm going to combine these with a log property. Okay, so if I'm adding two logs, that's like multiplying their arguments. I might go in and just for the sake of like showing all the steps, I'm going to go in and distribute there inside the log to get x squared minus 2x. And then at this point, I'm going to take 2 to both sides power to resolve the log. So 2 to the log base 2 of x squared minus 2x is going to equal 2 to the third. And what we know about logs and exponentials, they undo each other provided they've got the same base. So I'm going to say x squared minus 2x is equal to 2 to the third is 8. And then I'm going to set this thing to 0 and hopefully factor. It looks pretty factorable to me. Two numbers that multiply to -8 while adding to -2. It's going to have to be 4 and 2, probably x minus 4x plus 2. Okay, so we would say, all right, that would happen when x was equal to 4 or when x was equal to -2, right? And they want you to choose answer choice C, but we're not going to do that. We're going to be a little smarter. We're going to check for extraneous solutions. I'm going to say, all right, plugging in x equals 4 there and there is not going to cause me to take the log of a negative number, log of 0. So that's not an extraneous solution. But x equals -2, yeah, right there. That's going to be the log of a negative number, so that's game over. And so we're going to scratch that one out. That's extraneous. And because we're throwing that one out, it's going to be x equals 4 only. All right, the next one is talking about 8 to the x plus 7 as part of an equation involving other exponential expressions with base e. Which of the following is equivalent to 8 to the x plus 7 and is therefore more useful in solving the equation? So, okay, only one of these should be equivalent. Yeah, because they all got the same base. Yeah, I've seen one of like a problem of this type where there were actually different bases and you had to realize that only one of the bases was going to be useful in helping you solve an equation. But maybe that one's one that you're going to see soon. Okay, so what we need is to write 8 as e to a power, right? Because we're always starting over here with a base of e. And so it's going to be e to the natural log of something, it's based on the answer choices. And then hopefully that just reactivates. Oh yeah, they undo each other. So that's e to the natural log 8. Okay, that's the key understanding for this problem, is that 8 can be rewritten as e to the natural log of 8. And then what I'm going to do is I'm going to say 8 to the power of x plus 7 in parentheses is e to the log 8 to the power of x plus 7. And then we see right here, we've got power of a power. That's where we're going to multiply those powers. I'm going to say that this is e to the natural log of 8. That's just a number. I'm just going to hold on to it just like that. And then I'll have x plus 7. And what is going on here? I don't see any of these options, right? Okay, it's definitely not this because we can't just like allow part of an exponent to come down. We need log 8, not log of 2. This is definitely not true. That's just x plus 7, not 8 to the x plus 7. Okay, so it must be D. But if you're sitting there thinking, like, I don't really see how that works, what we would need to do is we would need to realize that 8 equals 2 to the third. So that the natural log of 8 was equal to the natural log of 2 to the third, and applying that that power property for logs, that we're going to say that's 3 times the natural log of 2. And then if I go over here and say that's 3 times the natural log of 2, maybe I need to write it as 3 times x plus 7 for you to see, okay, that's 3x plus 21. All right, I did not catch the language on this one. A regression is calculated. We don't know about that. I'd say this problem, if we just, I think what I'm going to do, I'll just kind of black those out a little bit. And if we just read what's left, f of x is a plus b natural log x, where a is positive and b is greater than 1, can be expressed as g of x equals this. Yeah, what's the value of c in terms of b? I really liked this problem. I just didn't realize that they were talking about regression, which is something we're going to hit later in the year in our AP Pre-Calc class. Okay, so a plus b natural log x. I'm going to write that, I don't usually do this, but I'm going to write it as log base e of x. And I need that to equal a plus c times log base 5 of x. Okay, and so really what I need is the relationship between b and c. So I'm going to subtract a from both sides of this equation and just kind of like not worry about that anymore. Okay, yeah. What I'm going to do is, yeah, I'm going to solve for c in terms of b. So I need to solve for b, pardon me, solve for c. What's the value of c? So I need to get that on its own. So I'm going to divide both sides by log base 5 of x. C is going to equal b times log base e of x divided by log base 5 of x. It's like, that's not any of my answer choices, right? That's not what I like to see. All right, so what we're going to do is say, I'm kind of confused here because they've got the same argument. All right, I have to admit, I sat and looked at this one for a couple of minutes and I was not immediately seeing what to do. I think what I'm going to do is do a change of base on log base 5 of x. I didn't actually take it all the way through. I just saw this and started recording, so at least I can think of something to do. I'm going to do change of base on this into natural logs. Remember, that would be natural log of x divided by natural log of 5. And yeah, that's good. This is going to work. Okay, I'm not sure. I'm sure there's a better way to solve this problem. And if you have found one, please come let me know sometime. Because I would love to see it. This one's very interesting. I'm not really sure what to do. And I know that's how y'all feel oftentimes. Okay, right here. So b times log base e of x, which I'm now going to go back to calling natural log of x. And then if I'm dividing by log base 5 of x, I'm multiplying by the reciprocal, right? So this is going to be, maybe I'll put blue parentheses around it. Right, but since I'm dividing, I'm going to flip it. So it's going to be natural log 5 divided by natural log x. These will cancel, and I'm going to get c is b times the natural log of 5. Okay, so that one was very tricky. All right, here we've got a table with x and y values modeled by the function f. Which of these could be f? Okay, well, 5/6 of x. That would fit the first two, but wait. No, because if I divided that by, I would need to have 20 in the 24 row. Okay, so that one's out. And plus, that's not an exponential or a log function. That's probably not it. 3 times 2 to the x over 5. That doesn't work with 6 and 5, I don't think. 3 times 2 to the 6/5? No. That's out. 5 times log base 6 of x. Oh, I should have noticed the same thing that I was supposed to notice on a bunch of these other ones. We're doubling the inputs while the outputs are adding. Okay, so that's plus 5, plus 5, plus 5. I was trying to match points, which I know is what a lot of y'all would do. Okay, so I know it's a log function, which I guess is what I had found by my process of elimination here. Okay, log base 6 of x. Okay, c fits the first one, but that almost makes me think that's not the right answer. Log base 6 of 12. That's not something we know. We don't know what exponent to put on 6 to get 12. Yeah, so that one's going to be out, and it's going to be this one. I'm going to go over here and say 5 times log base 2 of x over 3. So that would be log base 2 of 2. 12 divided by 3 is 4. 24 divided by 3 is 8. 48 divided by 3 is 16. Yeah, these are numbers that we can take the log with base 2 of. So I'm feeling confident about that and enough to make that choice and move on. If log base a of b equals 4, where a is a positive number and b is also a positive number, what's log base a squared of b to the 3? This is one I wish I'd seen before. I really like this. Okay, so what I'm going to do is I'm going to translate this one into its corresponding exponential equation. Okay, the base of the log needs to be the base of the exponential. Okay. The log is the exponent, so that's a to the 4. and that's going to equal the argument. Argument is the answer. Okay, so it's going to be like that. Or you could take a to both sides power on the equation I underlined in blue. Same thing, right? And so we get b equals a to the 4. Well, what I'm interested in is thinking about with respect to a squared. That's really, I think, what I need, right? Is I'm going to need a squared. Okay, so this means that a squared I would get by taking both sides to the 1/2 power. So that'll be b to the 1/2. Okay? And the log base a squared of b cubed is basically saying what exponent do I put on a squared to get b to the 3rd? Okay, so basically I'm going to need to get b cubed. What exponent am I going to put on both sides to turn that 1/2 into a 3? I'm going to be multiplying, and I think it's going to be 6. Yeah. So right in here, that's going to be 6, right? And so as a result, log base a squared of b cubed is that special exponent I put on a squared to get b cubed, and that's going to be 6. Now number 15 is giving us values of f for selected values of x where a and b and c and d and k are all real numbers. Okay, we've got this thing where a, b, c, and d are in ascending order, which are all greater than 1, and k is greater than 1. Which of these conditions would ensure that f is a logarithmic function? Okay, so the outputs being, they are adding, we're just adding k each time. Okay, yeah, so yeah, we don't see anything of that. Okay, so we need a to b and b to c and b and c to d to be multiplying. Whoops. So times something. And over here, times that same thing. Okay, so we're going to need b equals a squared. So maybe I think it's going to be d. This is my hypothesis at this point. Okay, if I had a squared, c is a to the 4, and d is a to the 8, what I'm doing is I'm multiplying both sides by, no, I'm like squaring the inputs. That's not quite right. Okay, so I was wrong. My hypothesis was not correct. Okay, but that's why it was just a hypothesis, so I was going to test it. All right, yeah, so I think a squared, a cubed, and a to the 4. I like that answer choice D. That was a good wrong answer. Yeah, each time we're multiplying by a in here. And so that is going to be a set of conditions that will ensure that f is a logarithmic function. Okay. I will also just point out, hey, I'm just adding k each time. All right, so over here, that's going to be answer choice C. And moving on. Okay, f is given by log base 4 of 16 over x. Of the following, solving which equation gives the solution to f of x equals 5? Okay, I don't really know what's going on with these equations, but what I'm going to do is I'm going to set f of x equal to 5. I'm going to start working on that, and, you know, hopefully one of these equations that's an answer choice shakes out, right? That's pretty much all I've got. So I'm going to set f of x equal to 5, so it'll be log base 4 of 16 over x equals 5. And okay, I would personally just take 4 to both sides power. But if you look at these answer choices, none of these have a 4 to the 5 in them, so obviously that's not what I'm supposed to do. What I'm going to do probably first is apply a log property. Right? If I can't do that, what else could I do, right? Apply a log property probably on that division on the inside of the argument. So I'm going to say that this is equal to log base 4 of 16 minus the log base 4 of x is equal to 5. Okay, that is none of these. Right, unfortunately, and now I'm looking to see. Oh, I'm just looking at them. Okay, I see which one it is. That's, oh man. Okay, now, what we're gonna need to do is, you know, kind of looking at having the log base 4 of 16 with a positive does mean I need to eliminate those two answer choices. Based on that, it's like, oh, okay, now they're talking about natural log. So I need to do a change of base formula on the x one, even though I just really don't see that as necessary at all. But if we're going to change bases, we're going to decide what our base is first. Okay, and base is going to be natural base, natural log. And then the number that goes in the argument of the numerator is going to be the original argument, the number that was higher in the first place. And the argument of the denominator is the base of the original. And that's going to equal 5. And that's why I've got answer choice B here. Number 17. M is given by m of x as log base 10 of e plus log base 10 of x to the negative 1. Which of these statements is true? Oh, m is increasing. The graph of m is concave up, and we're talking about some limits. Goodness. Okay. Well, I'm thinking about this. I think I'm going to approach this with the transforms. I'm also just going to immediately deal with that negative 1 power. I don't really like that there. So what I'm going to say is that m is now equal to log base 10 of e. Oh, no, but we're also adding these logs. So what I'm going to do is I'm going to say, actually, I'm just going to say log base 10 is implicit. So I'm just going to say log of e plus, minus, because I'm going to use that power property, which is basically becoming there, log of x. I'm trying to think which would be better for y'all. I think I should probably stay there rather than calling this, like log base 10 of e divided by x. Yeah, I don't like thinking about the fraction in there. Okay, well, that's all we can do. Now, log base 10 of e, that's just it's gonna be some number that is, it's greater than 0. It's a positive number, but it's really small, right? So you'd have to take some kind of root of 10 to get e. So I'm gonna say a small positive number. I'm just gonna call this k, just for ease. And if I've got, the graph of y equals some number minus the log of x, that's going to look like an upside down log graph. So it's going to look like that. And, it's going to be shifted up or down a little bit by k, but that's really not, I don't think that's what's important. M is going to be a decreasing function, right? Because I'm seeing negative slopes, or as I move left to right, the graph is going downhill. And it's concave up because the graph is smiling. Okay, so decreasing and concave up, oh, well, that's only c, so I don't even have to worry about the limit. As x approaches 0 from the positive side, yes, this thing is approaching positive infinity right there, so that's going to be confirming my answer choice. 18, I really liked this one. This one is really actually getting more towards what we're going to do in the next unit, kind of solving backwards for x in terms of y, but you could do this right now, right? You could totally do this. Which of these gives x as a function of y? Well, I think it's pretty clear that what happens to y is, oh, whoops, I didn't really catch that it was 1, 3, 5, 7, and 9 were the exponents. Well, the exponent keeps being like 1 bigger than twice x. So I think y is going to equal e to the 2x plus 1, and then add 4 on the outside. Yes, that's exactly it. And now our job is going to be to solve for x, out of this equation. So I've got an x right there, and I want to solve for it on its own. So I'm going to start by getting rid of that 4. So I've got y minus 4 equals e to the 2x plus 1. Then I need to get rid of that exponential, right? I need to get the x down out of the exponent, or really the 2x plus 1. So what I'm going to do, I'm going to take a log of both sides. I'm going to take a natural log of both sides because the base of the log should be the base of the exponentials. So natural log of y minus 4 equals 2x plus 1. Okay. Then I'm going to subtract 1, but I'm going to do it. Notice how they did it? Okay. Probably whoever wrote this one is also maybe an AP calculus teacher, and I like to write the added constant to the left side. So there's not any confusion about what's on the inside of the log and what isn't. Now, if you use parentheses judiciously, you shouldn't have to worry about it. But, okay, I've got that, and this is going to equal 2x. So x is going to equal, if I divide everything by 2, I'll have 1/2 natural log of y minus 4. But notice that is not one of my answer choices. It's like, okay, well, I'm going to eliminate a and b because I don't have the negative half. But of these, well, it's not regular log of y minus 4, so it must be this one. But what we're doing here, okay, I have solved for x. But remember that, a multiplier out the front of a log can be applied as an exponent on the argument. So that would be y minus 4 to the 1/2 power. That is the square root of y minus 4. Okay, so we've got ourselves a good answer here. Let's move on and do these free response questions. Okay. Now, I'm going to do as much as I can. I'm going to try to do these without a calculator because, your upcoming test, it does not allow the use of calculator, right? I just found this on AP Classroom and it said calculator. I'm going to try to be brave and not use one. I might not show the calculator on screen because that really slows down the recording process and I got to do a bunch of stuff today. So I'm going to try to do as much as I can on screen and then I'll just describe to you the other things. All right, so I think really the key here is that S of D is A times B to the D, where S is the noise level in decibels and D is the distance. Okay, use the given data to write two equations to find the constants A and B. All right, so this is one of those exponential ones, and we're going to set up a system. So when D equals 0, noise level is 105. So S of 0 equals A times B to the 0. And we know that S of 0 is 105. Okay, so that's telling me A equals 105. So a system was not necessary. Then S of 100, that's going to be A, which I now know is 105, times B to the 100. That's going to equal, what do we say? That's 49 decibels. I thought sound was a log growing thing. I'm just going to trust this. D meters from the turbine. Maybe this particular wind turbine has sound that is modeled by exponential decay or something, and I'm sure that's fine. I thought it was inverse square. No, that's what it was. Is that noise is or sound is oftentimes an inverse square situation, but inverse square, if you graph it versus exponential decay, it's not all that different. Okay, so now I see what we're doing. So b to the 100th power equals 49. As a result, I'm going to say b is the 100th root of 49. Oh, no. I did not divide by 105. Yeah. Okay, so, and that's a number. I didn't have to use a calculator for it. Two equations that can be used to find the values. Okay, I didn't really emphasize that. When they're talking about two equations, we already did it. It's a times b to the 0 equals 105, and a times b to the 100 equals 49. Those are the two equations they're talking about. And then find the values for a and b. Okay, well, I've found those. Maybe I'll just kind of underline in red. A is this, b is that. Okay, happy. Let's keep it moving. Use the given data to find the average rate of change of the noise level in decibels per meter from d equals 0 to d equals 100. Well, they gave us both of these. Yeah. So it was 105. Oh, wait, no. D. S of 0 equals 105. S of 100 equals 49. So that means that average rate of change is y2 minus y1 divided by x2 minus x1. All right, so 49 minus 105. Well, if it was 50 minus 105, I'd be having negative 55. So I think this is negative 56 divided by 100 is negative 0.56. Okay. Now, the units, which I'm going to use to help me, to estimate, that's nice. Okay, anyway, I'm going to let the units guide me. Okay, so S is measured in decibels. That's the abbreviation. Per meter. Okay, so each time the distance increases 1 meter, we are expecting the number of decibels to decrease on average 0.56 of a decibel. Okay, so Oh, I guess that wasn't m, that was d. This time distance increases 1 meter, s decreases 0.56 decibels on average. Okay. Then we're going to use the average rate of change found in the first part, that negative 0.56, to estimate the noise level in decibels at a distance of 120 meters. Okay, so the actual noise level was 49, and then I'm going to add, okay, it's like the total amount of change. Well, that would be the average rate of change, negative 0.56 decibels per meter, times the additional 20 meters from the 100 meters to the 120 meters. And okay, I think I can do this because if I multiplied the negative 0.56 by 10, that would be 5.6. So if I doubled that, that would be 11.2. So 49 minus 11.2 is going to be 37.8. Yeah, 48, 49, yeah. Then we're going to use the model S to find the value of M such that the noise level is 20 decibels at a distance of m meters. Okay, I think that was an earlier problem that was where m was the actual function. All right, so S, we've actually got the formula for it, and we want to find out when the noise level is 20. So we want to solve the equation S equals 20. All right. So we found that S was equal to 105 times, now I might call this 49 over 105 to the 1 over 100th to the t, and then multiply those exponents. I think that'll be a good way for me to go. All right, then, and y'all are probably not gonna like this, but I think what they envisioned was you graphing this function, graphing 20 and finding the intersection and reporting that value. But I'm just gonna solve this one exactly, right? I'm gonna say 20 is the sound level equals 105 times this 49 over 105 to the t divided by 100 power. So then I'm going to say, all right, keep solving. 20 over 105 equals 49 over 105 to the t divided by 100. Then I'm going to take a log of both sides. Okay, I'm going to take a log with the base of the log needs to be the base of the exponential. So this is log base 49 over 105. It's a weird base for a log, but it does work. 20 over 105. That's equal to t divided by 100. So as a result, I'm kind of running out of room here. So I'm going to multiply both sides by 100 and say, okay, I also need to get rid of that arrow. 100 log base 49 over 105 of 20 divided by 105 is equal to t. And they would not ask you this without a calculator because there's just like such a multitude of different correct answers. I can see why this one would be a calculator question. Right, this next one also allows the use of the calculator, but I don't think it will be as, I still don't think I'm going to need it. Determine the end behavior of f as input values increase without bound. Okay, this is exponential growth because of the 1.02 being bigger than 1. As a result, I can say that the limit as x approaches positive infinity of f of x, well, that's going to go to infinity. So that's exponential growth. And then as values of x increase without bound, that's the only one they asked me about, right? They didn't ask about as x decreases without bound, so I'm not going to tell them anything about it. Determine the end behavior of f as input values decrease without bound. Oh, okay, so I thought they were going to ask me about g's end behavior. Who knows? Maybe that's coming up. All right, so the limit as x approaches negative infinity of f of x. Okay, well, as x approaches negative infinity, this part that I'm highlighting, the actual exponential part, that's what's going to go to 0, right? Because I'm taking negative powers of 1.02. That's going to be 5 divided by, positive powers of 1.02. And as those powers in the denominator get bigger, as x approaches negative infinity, that thing's going to be, 5 is going to stay constant in the numerator, denominator is going to grow, it's going to go 0. So then I'm going to be approaching, negative 1 plus 0. And then that's just going to equal -1. And we expressed our answer using the mathematical notation of a limit, which is something that I think you need to be practicing. I did tell somebody I was going to have like a limit workshop or something, limit notation workshop. We still can't do that. We'll probably do that sometime before the semester exam. So determine the end behavior of g as input values of x decrease without bound. Okay, I'm going to go, that's natural log of 3 minus x. I'm just going to copy that in here. Okay, now if we are going to try to figure this out, we haven't, at least in my sections, I have not been really talking about log of a negative, stuff like that. Not really what we're interested in. Oh, wait, I was going to apply log properties to this, and there is no log property for this. So, what I'll say is I think this one might be a little bit out of bounds for what we've been doing, for like the type of log functions we've been working in my pre-calc class. But I'm sure there's going to be some way that we can look at this as values of x decrease without bound. Yes, I think I know what to do with this. So decrease without bound, that's x approaching -infinity. And as we go towards -infinity, what's going to happen is, well, I'm going to be taking 3 minus a large negative number. And so I need to think about what happens to the natural log of a thing as that thing gets really big and positive. Well, the graph of y equals natural log of x, it grows without bound. It doesn't have a horizontal asymptote. Its limit is positive infinity. And as a result, I'm going to say this one's going to have a limit of positive infinity as well. Because it's basically natural log of something that's going towards infinity. You know, what exponent do I have to put on e to obtain a number that's getting close to infinity? You're going to put a really big exponent on e, right? So that's why this one's positive infinity. Input values that are less than 3 and sufficiently close to 3. I believe that means approaching 3 from the negative side. But let's think about this. As we approach 3 from the negative side, like 2.9, 2.99, 2.999. Yeah, think about 3 minus those numbers. That's log of 0.1, log of 0.01, log of 0.001. This is like thinking about the graph of y equals regular log x, or log of regular x, as the input of that regular log is going towards 0. And we know that one goes -infinity. So I'm going to say that's -infinity. I didn't just love my explanations for this part B, but that's what I've got for you. All right, and now we're going to figure out the values of x for which f is greater than g. And I do think that this one is going to require a calculator. All right, so I pulled out the calculator. I've got this thing graphed, and I want f greater than or equal to g. F I've got in y1, g I've got in y2. Let's zoom to the standard window and see what's going on here. Okay, so what's the actual equation there? -1 plus 5 times 1.02 to the x. Okay, also, notice, okay, I've got, like, this is a vertical asymptote here. Oh, also, if you had a calculator, these in behavior questions would have been much easier. You could have just zoomed out and kind of looked at the overall behavior. That's what you were supposed to do. Okay, I was just trying to do too few things with the calculator. All right, so I need to figure out where f is greater than or equal to g. Yeah, so that's going to be where the blue curve is above or equal to the red curve. And so I'm going to need to be, seeing over here to the left of what I can. So I'm going to actually go from -20 up to 0, because I already know, oh, whoops, I don't want to go -200. I don't think that will be necessary. And then we're going to go down to just 0, or up to 0. Okay, and I'm really hoping that the intersection is going to happen on this window. Okay, because the exponential, yeah, that's just an increasing function, and that log function is just decreasing. So what I need to do is calculate the intersection blue curve, red curve, give it a guess. And that is my guess. Okay, and then x is going to be negative 13.674. Okay, and if f is greater than or equal to g, that's where blue is above red. So that's going to be after negative 13.674. So x is greater than or equal to that number. Remember, always 3 decimals in this class. Right, and then number 21. Here's the actual directions that are on the, I've talked about this before, I don't think I've ever actually shown them to you. This is what is clipped and put into the free response booklet on number 4, where you actually have to simplify your answers. This is what I was talking about, where with the simplifying our answers. So yeah, you can read through that. Rewrite g in the form g of x equals 7 to the c, where c is a constant. Well, g is just a constant. Okay, so that's going to equal, well, in top, I'm going to have 7 to the 3 plus 4 divided by 7 to the 6. So that's 7 to the 7 over 7 to the 6. Okay, I would subtract those exponents, and that's just going to be 1, 7. Okay, so that means that c is 1. Okay. Then we're going to rewrite h of x in the form of natural log of a plus b natural log of x. All right, so h of x. Notice that the cube is on the entire argument, right, of 2x. So I'm going to swing that around first, right, because it's on the outside. So I'm going to say that's 3 times the natural log of 2x. Then inside, I've got a multiplication on my argument, so I'm going to write that as the sum of 2 logs. Also, they prompted me for a sum of 2 logs. Okay, but there's kind of a trick here because, we're still multiplying the whole thing by 3. And it said, okay, so that's going to be 3 log 2 plus 3 log x. But they wanted log of a plus b log of x. We can't have this 3 on the outside here. So what we're going to do is we're going to apply that as an exponent right there. And then I'm kind of running out of room here, but I'm going to say this is equal to natural log. Pardon me, I've been saying log for natural log a lot. But it's true. That's the only log I do care about. Natural log of 2 to the third plus 3 natural log of x. So I'm going to just say, I don't know if that's what they're looking for. It's a, progress check question, so I would have to go in and score your work anyway on the free response. I'm going to say a is 8 and b is equal to 3. And kind of just leave that there. All right, part B, functions j and k are given by j of x equals this and k of x equals that. Solve j of x equals 5 to the 16, gladly. 5 to the x to the 3, I'm going to multiply those exponents right now, times 5 to the 5 is equal to 5 to the 16. I'm going to add my exponents because that's what we do when we multiply things with the same base and different exponents. 3x plus 5, that's 5 to the 16. Now in Algebra 2, we were oftentimes like, oh, well, if these expressions are the same, well, then clearly their exponents have to be the same. But really what we're doing here is we're just taking the log with base 5 of both sides, and I think you're all ready to hear that now. So if we take the log with base 5 of both sides, it would just kill off the exponentials, and I'd say 3x plus 5 equals 16. Subtract the 5 and get 3x equals 11, and then get x equals 11 divided by 3. Okay, that is values of x in the domain of j. Everything's in the domain of j, so I don't think there's really anything for us to be worried about here. And then, let me think. Okay. I feel like I had something else to say about this. Oh, but no, that's all right. Okay, part 2 of part B, section 2 of part B. K of x equals natural log of x. All right, so I'm going to say 2 natural log x minus natural log of 2x. That needs to equal natural log 8. Okay, so what I'm going to do is I'm going to be combining these with log properties and then eventually taking e to both sides power. I think the first thing I see this and that. These are both things I'm going to want to be looking at. All right, anyway, I'm going to say, all right, so this is going to become an exponent, x squared minus natural log of 2x, and that'll equal natural log of 8. Okay. Then what I'm going to do is I'm going to apply the log property and say, all right, I'm going to divide the arguments x squared divided by 2x. And that's going to equal natural log of 8. Now I can take e to both sides power to get rid of those natural logs. And well, I would say e to those things will be equal, and then they undo each other. And so I've got x squared divided by 2x equals 8. So that's giving me x squared equals 16x. Pardon me, I was looking at something else. And all right, x squared equals 16x. Yeah, okay, I'm actually going to solve this one because this hasn't happened yet on any of the problems we've worked. I'm going to solve this one by factoring, not by dividing both sides by x. If you divide both sides by x, you have to think about what if I just divided both sides by 0? Was that actually a solution that I just got rid of? And it would have been, except it would have been an extraneous solution, so I'm just going to keep factoring. Okay, so that's going to be x equals 0 or x equals 16. X equals 0 is not in the domain of k, right? Because I'd be taking a natural log of 0. So that's an extraneous solution, and I'm going to get rid of it. Right? X equals 16 only. And then, okay, I haven't done part C yet, but I'll do that once I get over here. I'll just move that out of the way, I guess. All right, part C, over here. M is given by this function, which is, oh, interesting. I was wondering if they wanted us to solve this type of equation. This is one that we solved in my Algebra 2 class last year, but I never saw any of these in AP Classroom. Okay, so I'm glad that we're seeing that this is a possibility. What we need to do is set m equal to 0. 2 to the x squared minus 7 times 2 to the x plus 6 equals 0. Okay. This thing is factorable. It just doesn't look like it. What I'm going to do is I'm going to say, all right, suppose t equals 2 to the x. Okay. Then I'll have t squared minus 7 times t plus 6 equaling 0. Okay. This is factorable, right? This is going to be t minus 6 times t minus 1. Okay, and then that's going to be either t equals 6 or t equals 1. But remember, the input values of this thing are x's, and t equals 2 to the x. So I'm going to go back here and undo my substitution. 2 to the x equals 6, or 2 to the x is going to equal 1. Okay. I think on the right, we can solve this one with our eyes. This is going to be x equals 0, and that is in the domain of m, right? M has no restriction on its domain. There's nothing we can't put as an exponent. And then over here, 2 to the x equals 6, I probably need to take a log with base 2 of both sides. So I'm going to say log base 2 of 2 to the x equals log base 2 of 6. And so x equals log base 2 argument 6. These are my solutions, or my input values in the domain of m that yield an output value of 0. And that was nice. I like that. Okay, now the last thing I've got these two inequalities. And, well, yeah, I think I will have time to do both of them. Find the values of x that make the inequality true. Maybe you just watch me do this one, and I'll do the second one a slightly different way for 403 in my class that was talking to me about other ways to solve these. I think what I'm about to do is definitely going to be like the officially approved technique. Okay, so step 1, use log property. This is going to be the natural log of x plus 9 all divided by x squared minus 4x minus 5. Okay, now I need to take e to both sides power. So I'm going to say, e to the natural log, that's just the argument. X plus 9 over x squared minus 4x minus 5 is greater than e to the 0, which is 1. Okay, now I need to set this thing to 0 because if I multiply both sides of the inequality by x squared minus 4x minus 5, I'm going to be losing out on a bunch of stuff because that denominator, sometimes it's positive, sometimes it's negative, so we'd have to devolve into cases, and I really don't think that's what you want to do. I'm going to ask you to trust me on that. I've never shown you what that looks like, but I promise you it's worse than what we're doing here. So I'm subtracting 1. And now I'm going to be subtracting an x squared minus 4x minus 5 over x squared minus 4x minus 5, because I know I've done enough of these that I know what's happening here, right? Hopefully you have too. Ideally, you have done more of these than I have, because you did this on the homework and on the quiz, and I didn't make the keys for either of those things. So I don't have quite as much experience as you hopefully have. So in the numerator of our combined fraction, we're going to have x minus 9 minus x squared minus 4x plus 5. And in the denominator, I'm just going to have, wait, there was not a plus there, that's a minus. X squared, negative 4x, and negative 5. And this is still going to be greater than 0. Then I'm going to actually subtract. Okay, I'm going to have a negative x squared. X minus negative 4x is going to be positive 5x. 9 minus negative 5 is positive 14. Okay, yeah, that's going to be factorable. Over, and now I'm kind of running out of room here, x squared minus 4x minus 5. I'm going to factor that one now. X minus 5x plus 1. And we're interested in where that's positive. We're closing in on, getting close to an answer. So what we're going to do, we're going to factor out the numerator. So that's going to be the negative of x squared minus 5x minus 14. That's going to be x minus 7 times x plus 2. X minus 7 x plus 2. And we're going to divide by x minus 5 and x plus 1. And we're interested in where this is positive. So I've identified my key numbers. Now I've factored the numerator and the denominator after setting the inequality to 0. So that's going to be x equals 7, x equals negative 2, x equals 5, and x equals negative 1. Make myself a number line. Negative 2, negative 1, 5, and 7. Okay, now I'm going to choose a test point. Me personally, I'm always going to choose 0, right? And I think that would be the easiest thing. When x equals 0, I'm going to have the negative of negative 7 times positive 2. That's going to be a positive number on top. Over negative 5 times positive 1, that's a negative number in the bottom. And so I've got positive over negative, that's going to be a negative. If I look back to, this expression here, which is kind of what I'm testing on, I don't see any double roots or any multiplicities at all besides 1, so I know that I'm always going to be seeing a sign change at every key number. So positive, negative, yes, sign is changing. I'm interested in where this thing is less than 0, or pardon me, greater than 0, right there. So that's positive, so it's going to be here. Not at any of these actual key numbers, because either vertical asymptotes on the thing in yellow or there's zeros. Either way, it's not a place where it's greater than 0. All right, so my hypothesis is negative 2 to negative 1. And 5 to 7. But I have to trim on that hypothesis based possibly on the domain of these logs. So on a domain level, I need x plus 9 to be positive. So that means x is greater than negative 9. Well, all of these values are greater than negative 9. So I just need to be worried about the x values that are less than negative 9 or equal to negative 9. And that's not going to happen, so I'm not going to eliminate any intervals based on that. Okay, the other thing that can happen is I need x squared minus 4x minus 5, which I'm going to factor x plus 1. I need that to be positive as well. And yeah, I don't know if you solve this with a number line, negative 1 and 5. I think that's a little much. I don't think you need a number line to solve a quadratic inequality, because we know what the graph looks like. Okay, so we need x to be less than negative 1, which it already is, or greater than 5, which it also already is. Okay, so that was all for nothing, all that checking. I did not end up Yeah, I didn't need. Yeah, it wasn't. I didn't end up subtracting on anything. But my final solution is -2 to -1, and also 5 to 7. So we know these are pretty involved problems, right? We know they're not gonna have to do these a whole lot. Probably just once on any sort of upcoming assessment. Okay, on this one, I'm gonna do this one a different way. Okay, way that was suggested to me by a student. And so if the difference of the two logs is positive, then this log of x plus 10 has to be greater, right? Otherwise, if it wasn't, then the original inequality wouldn't be true. Okay, now what I'm going to do, I'm going to take e to both sides power. So I'm going to say x plus 10 is greater than x squared minus 2x minus 8. Okay. Now I'm going to set this thing to 0. And I'm going to say 0 is greater than x squared minus 3x minus 18. And hey, look, this thing is factorable. So this is 0 greater than x minus 6 times x plus 3. I'm going to give a sketch of this thing, but if you wanted to do, a number line and do test points, that'd be fine. I just don't think that's necessary for a quadratic, like I just said earlier. Okay, we're interested in where this is positive. I didn't really like the look of that. Didn't look all that much like a parabola. And there we go. Okay, so I've got myself a parabola, and then I'm interested in where, the output value, the y coordinate, if y equals x minus 6 times x plus 3, which it does, so I'm sketching this graph, I'm interested in where it's positive, right? Greater than 0. Nope, that's not what I want. I want where 0 is greater than, so I want the intervals on which this thing's negative. Okay, so -3 to 6. Okay, but now I need to consider the domain. I need x plus 10 greater than 0. Okay, well, that means x is greater than -10, which it already is. Okay, so I'm good there. But then I also need x squared minus 2x minus 8 to be greater than 0. And so that's something I'm going to need to look at. I'm going to say, all right, this is going to be x squared. No, I'm factoring. That's what I'm trying to do. X minus 4 times x plus 2. All right, so I'm going to have a parabola with zeros at -2 and positive 4. I need this to be greater than 0 so that I'm not taking the log of a 0 or a negative number. So I'm interested in where x is less than -2. Okay. Or when x is greater than 4. Okay, because I know that these always end up having like basically two intervals. It's like, how is this going to happen? Okay, so what I need to do is I need to get rid of all x's between -2 and 4. So I'm going to kind of sketch this out for you. If we're saying we're between -3 and positive 6, but we need to cut out the values from -2. Let me think about it. I'm just going to label this here. -2 to -4. These need to all be gone. What that means is that I'm just going to be going from -3 up to -2, and from 4 to 6. Or from, wait, no, that was positive 4. I don't know why I put a -4 there. That would not make sense. -4 is not greater than -2. But all the same, here I've got myself, my actual answers are in here. So that's -3 up to -2, union 4 to 6. Okay, so that's another way to solve this type of problem. But either way, we have to be considering the domain. Okay, but that was a extremely long practice session. That was a lot of practice problems, long video. That's going to be all for it. Thanks for watching.